my dose, remember for phosphorus, I need to record 110 to the 15. So when we did this, you cannot do the low temperature solid phase Fe. So I have to go to the furnace. So in this case, the guy had no choice, so he did two kinds of annealing. One is at 900 degrees for 3 hours, and the other is 1200 degrees for 3 hours. So there are two anneal thing, and the substrate is P-type. So this is very simple problem. I took a P-type substrate, I came with 50 keV implant with this dose, right? So question is, what does it do? Okay, what is happening when I anneal it? How bad is the annealing case? So very easy way to see is that first you get the D values. At D values for phosphorus at 1200 and 900. So this is just to show you how you look at this situation. So you got the D value which you can read, right, from the table. Then, because I know the energy, I can reach the RP and delta RP. One is 750 angstrom, one is 275. This is all instantaneous the moment you have this condition. Now what you do, you get a DT product. DT product is important. This is the length over which this thing will diffuse, right? You want that to be as small as possible, so you can, whatever you implant, you want to end up with essentially that, not a whole different profile, right? So if you do the DT product with all this information here, you get a 288 angstrom of DT product here, right? Okay, now delta RP is your this guy, right? Let me see here. See, this was your delta RP, right? This was the initial implant. Now when I'm doing annealing, this thing is stretching, right? And my peak concentration is coming down. And this is like 2 square root of 2 dt. So like my standard deviation of the implant as if it got increased. So this your final profile is dictated by this delta RP, plus you got an additional 2 is the square root of 2 dt, because this is the unit of length and this is the unit of length. So that's kind of what happens, right? So now if I go back to this problem, so delta RP was 275, right? But look at the dt at 900. Okay, this is 0.02 micron, this is 0.02, so 2 square root of 2 dt, it's on the same order. I mean, it's still not very desirable, but at least it's like 0.02 was your projected range, and then you just added this much there, right? Because you delta RP was when you were implanting, but then on top of that, I added 2 square root of dt. So there is a spread, but it's in the same ballpark. But now if I did the annealing at 1200, look what happened to dt. It is 1.1 micron, 11,000 angstrom, correct? So this will be totally unacceptable, to make any device, because the spread will be so large here, right? Okay, so this is to tell you that if you don't do the implantation for amorphization, you are stuck with these kinds of annealing temperature, and even the very low annealing temperature and time may be unacceptable, because you want to keep the delta RP and 2 square root of dt as small as possible, Delta RP, you cannot do anything because that's your implant, but you can do a lot about the 2 square root of 2 dt. So this is what this is, but now question is, how do I know quantitatively? So one thing that you need to recognize is this is what happens. You implant, your dose is fixed, right? When I'm annealing, there is no additional atoms, so the area of this curve and this curve needs to be the same. So I will have a drop in this concentration, so NP will become NP prime, okay? And your delta RP will become delta RP prime, okay? So that's what will happen. And then the rest of the equation remain the same because they're both Gaussian profile, right? They're both Gaussian profile, but only all you have to do is to change NP by NP prime and delta RP by delta RP prime. So we'll talk about what those changes are, and that's it. Then you can do the whole thing. You can very quickly calculate the final profile. So if you go, so this is what I'm showing you here a little bit, that because there is an added square root of 2 dt in your range, so you basically replace the delta RP square by delta RP square times square of this. Okay, so you replace the delta RP prime will be your original delta RP when you implanted it, RP square plus 2 dt, right? Because units are same. Square root of 2 dt is centimeter, right? And this is also same unit. So but you sum the square of this. This is important. So delta RP square becomes the old delta RP plus 2 dt. That's the only thing you need to do. So if you know the dt product of your annealing, you already knew delta RP, you know delta RP prime. And once you know that, the whole game is very simple. Then you go calculate your new concentration, which is NP prime. What is NP prime? This is the old equation. Q is the dose, the square root of 2 pi and multiplication by delta RP. That was your original. All you have to do is to replace this by delta RP prime. So all you needed was dt, right? RP was known, you just calculate this new delta RP. Immediately it gives you the new surface concentration, okay, which is basically written here. So I just replace this by this will be basically square root, right? Because delta RP square is this. So delta RP will be square root of this guy, correct? So that's what this equation is. Okay, and then if you remember the new junction depth will be exact same equation, RP plus or minus delta RP square root of 2 ln of NP divided by NB. This was my original equation which we talked early. So all I'm going to do is to just replace the delta RP by delta RP prime, okay, and then NP by NP prime. That's it. So now you know in a very quick time what is your final thing, including the annealing. Because implantation is not what you end up getting in the end. There is, I mean, if you're lucky, if your dt is negligible compared to delta RP, then your profile is, and this is what people are trying to do, to make the dt so small that there is very little perturbation between that, right? But you have to go to some temperature, right? Because you need to heal the lattice and you need to activate the dopant. Okay, so this is a little bit of the text about these kinds of things. So, and this is the one example, but this is the, so basically what you see is that in the final answer I gave you here, that at 900 degree your junction depth became 0.28 micron, right? Okay, so your junction depth, but at 1200 degree junction depth was way out of line, 5.6 micron. So because when you calculate this, it is very, very high, and 0.28 is unacceptable. I'm looking for 0.02, you remember? But here I was forced to do this because there was no way I could anneal, because I did not choose my conditions of energy and implant that will allow you to go through the amorphization. Right? So these are some basic concepts. Okay, so this is the same thing I'm repeating, making it a little more clear for you here, that the new delta RP square is the old delta RP square plus 2 dt. Okay, this is the key transformation you have to make, right? And then the whole thing is very simple. Then NP prime is your dose divided by this. Simply you replace this, right? This is same equation, and your profile then becomes your new NP. This is your NP prime, right? Exponential of minus x minus RP square but instead of 2 delta RP square, you will put this. So the profile is very simple, right? You're only making this transformation delta RP. This is your delta RP prime, right? So this is your new profile after anneal. This is your new surface concentration after you anneal. And if you had the doping here, you can calculate the junction depth. If this was my doping, this will be the junction depth before, and this is the junction depth after. Right? Is that clear, guys? Okay. Okay, so how this thing is done, the rapid thermal annealing, and this is one of the greatest discoveries